Okay, we're doing the circular motion practice problems number 2. Here we're driving again, and we're going over a bump in the road. So we have so it's something like this. All right, going over this bump with a radius of 35 meters. That circle that would be created by the curvature of the road there, and we're going 12 meters per second. So if we look at the forces on the person here, what we have is just a normal force up and a weight down. Because we're in circular motion, the acceleration has to be towards the center of the circle. In this case, it's down. That tells me that the normal force must be less than the weight. So I'm going to make positive towards the center of the circle because I always want it in the direction. I always want it towards the center of the circle, so my acceleration is positive. So my F net is mg minus n, which is m times a, and I'm going to use v squared over r for a here because I'm interested in the v, or I have the v. So the apparent weight is your normal force, is the normal force acting on you. So if like when you're in the elevator and the elevator accelerates up and the normal force gets bigger, you feel a little heavier. That's because of the normal force changing, not because of your weight changing. So here what we have is the normal force is, if I solve for it, m times g minus v squared over r. I just moved that over and factored. So it's actually less. So I mean, I'm sure you felt this when you go over a bump. You sort of feel lighter. You feel like you get up out of your chair. Well, that's because the normal force on you is decreasing. So that's what it takes for you to go across this thing in a circle. So if we plug in those numbers, we get 394 newtons. This is that's a little less than 60% of your normal weight, or 6% of your weight, rather. So you're going to feel quite a bit lighter as you go over this curve at 25 miles an hour. If we want to know how fast we can drive over this without leaving our seat, we need to go back and look at the force diagram there. If I go over faster, now the mg never changes because my m and the g don't change. But if I go over faster, I'm going to feel even lighter. So that normal force is going to get smaller and smaller until ultimately n is 0 at the fastest speed. If I try to go any faster than that, what's going to happen is that and the car really, are going to fly off the bump here because the force down is not enough to keep us in that circular motion. We'd need to be like held down onto the road to make that circle, so we're not going to successfully make the circle. If it's a horizontal circle, you're talking about slipping towards the outside of the curve. Here it's a vertical circle, you're talking about going higher instead of going down over the curve. You're just going to fly up over it. So the F net's pretty simple once you make that realization. And I just can solve for my v pretty quickly. So that's 35 meter curve, 10 meters per second squared. The units work out nicely, and I get about 18.7 meters per second. So I'm getting the way, sort of part of the way there here. So when I started, I was only 60% of my normal force is only 60% of my weight. If I keep going from 12 meters per second to 18.7, then I'm going to feel weightless as I go over. I'm going to be in free fall, basically. Anytime you're in free fall, you sort of feel weightless. You feel like you're floating, because you kind of are. And so for the folks in the space station, they are weightless, not because they don't have any weight, but because they're in free fall towards the Earth. So does that change anything for the coffee cup sitting on my dash? Well, the only difference really between the coffee cup and me here is the m, and we saw that the m cancels out. So really, there's no difference there. I'm assuming that neither of us is subject to any additional forces here. If we had I've had harness holding me down, or the coffee cup is glued down or whatever. But if you're just sitting there on the stool, the m cancels out, and the car would fly up, I would fly up, the coffee cup would fly up if we went any faster.